Good afternoon, everyone. I hope you've all had a great lunch, and I also sincerely hope you cleared your plate like you were taught to. I'm pretty sure a lot of you have noticed the immense food left behind in LG7, Einstein Cafe, in the LSK building, but have you ever thought about what happens to this food that you don't finish? Just to give you an idea, some 40% of all the food produced in the United States is never eaten. In Europe, they throw away a whopping 100 million tons of food every year. This makes an unbelievable 273,000 tons of food every day, 11,415 tons per hour, and 190,000 kilograms per minute. After not having finished your lunch, the food will most probably get thrown out and end up in one of the many landfills in Hong Kong, which is also a home to many other materials such as concrete, plastic, e-waste, etc. The total daily food waste in Hong Kong is around 3,337 tons, of which 1/3 is from the commercial and industry sector. The food waste from this sector has increased from 400 tons in 2002 to 809 tons in 2012 and has finally increased to 1,003 tons in 2014. This form of disposal is not sustainable at all. Food waste in landfills, which is an organic waste that can decompose easily, is a complete waste of possible resources. When decomposed, food waste forms numerous products, namely methane, carbon dioxide, raw materials for fertilizers, etc. This process is more formally known as composting. Composting is a natural process of decomposition and recycling of organic material into a rich soil amendment known as compost. The substances that can be composted include fruits, vegetables, dairy products, grains, bread, unbleached paper napkins, coffee filters, eggshells, meats, newspaper, and the list goes on and on. Food waste consists mainly of these substances and hence is perfect for composting. Composting is a very lengthy process and can take anywhere from 3 months to 1 year. However, it is easy and can be done by everyone. First, you need to collect materials until you can make a pile that is at least 3 feet deep. Then, you need to sprinkle this pile with plenty of water and occasionally stir this in order to incorporate oxygen. When the material is dry, brown, and crumbly, you are ready to feed your garden. There are several factors that will affect the composting time: amount of waste, climate, composition. When it's hot, moist, and the compost has a good ratio of carbon to nitrogen, from 20 to 1 up to 100 to 1, a 3-month decomposition is very possible. This will, however, also require a critical mass to be built, which is usually a pile that is at least 3 feet deep. Doing this is several times better than just throwing the scraps out. Just think of all the benefits for the environment and your garden. Wait a minute. Hong Kong people don't even have gardens. Even though Hong Kong has the perfect climate for composting, it wouldn't really work since Hong Kong is a city revolving around tertiary sectors and lacks the space for these leisure activities. Though the concept of composting would still be a very suitable way of dealing with the 41,792 kilograms of food waste produced every hour, we would still need to find a way to make composting of food possible for people living in town, where gardens are unavailable. How would this work? Well, instead of composting the food waste at home, we can create a centralized space where food waste composting takes place. This centralized space would do well in the New Territories area compared to the urban areas in Hong Kong because there is more space available there. But even if we have the optimal conditions, it will still take at least 3 months. Can you imagine the storage capacity necessary in order to store 75 million kilograms of food waste? I think we need to take a different approach. Both our process and the existing ones are based on anaerobic digestion, which is defined as following. Anaerobic digestion is a proven, safe biological process where organic materials are broken down by microorganisms in the absence of oxygen to produce renewable energy and a nutrient-rich biofertilizer. We could use anaerobic digestion to not only minimize the time required in order to process the food waste, but also increase the beneficial products produced during the process. The major difference between anaerobic digestion and composting is the presence of oxygen. However, anaerobic digestion also produces far more useful materials. As the food waste anaerobically decays, it seeps methane, which is a key component of biogas. There are 4 major steps in anaerobic digestion: hydrolysis, acetogenesis, acetogenesis, and methanogenesis. These processes will produce different chemicals depending on the input. In the first process, which is hydrolysis, sugars, amino acids, and fatty acids will be produced if the inputs are carbohydrates, proteins, and fats respectively. In the second process, which is acetogenesis, sugars, amino acids, and fatty acids will form several different products, including carbonic acids, alcohols, hydrogen, carbon dioxide, and ammonia. In the third process, which is acetogenesis, the products formed in the second stage will react to form acetic acid, carbon dioxide, and hydrogen, and will finally react to form biogas in the last process, which is methanogenesis. In anaerobic digestion plants, the single or two-stage reactor approach may be taken. In single-stage reactors, these processes take place in the same reactor. Whereas in the two-stage reactor, hydrolysis and acetogenesis take place in an initial reactor, and then the acids formed are used by methanogenesis in the final reactor. The first phase will maintain a low pH for 2 to 3 days, whereas the second phase will maintain a pH ranging from 6 to 8 for 20 to 30 days to produce methane. The yield of biogas is dependent on several conditions: temperature, processing system, and its properties. Since it is a bacterium, it will function best at temperatures ranging between 35 to 50 degrees Celsius. The anaerobic digestibility and biogas and methane yields of the food waste were evaluated using batch anaerobic digestion tests by CENG R, performed at 50 degrees Celsius. The daily average moisture content, which is denoted by MC, and the ratio of volatile solids, which is referring to the portion of total solids present that have a caloric value, or, more simply, the portion of total solids that can be digested by the bacterium to total solids, which will be denoted by VS over TS, determined from a week-long sampling were 70% and 83% respectively, while the weekly average MC and VS over TS were 74% and 87% respectively. The nutrient content analysis showed that the food waste contained well-balanced nutrients for anaerobic microorganisms. The methane yield was determined to be 348 and 435 milliliters per gram of volatile solids respectively after 10 and 28 days of digestion. The average methane content of biogas was 73%. The average volatile solid destruction was 81% at the end of the 28-day digestion test. Currently, the Hong Kong government is concentrating on increasing the awareness of people and industry about the positive effects of separating food waste, but this will require a long time as it involves changing the mindset of people and corporations. That's why they are thinking of introducing fines similar to that in Europe. In Europe, people will be required to pay a fine if they do not separate their food waste. People in Hong Kong hate having to pay fines and will hence be incentivized to separate their food waste. Hong Kong government plans to build several plants in the next 10 years, a series of plants that will be able to process 1,300 to 1,500 tons of food waste per day. The plants will be called Organic Resource Recovery Center, or ORRC for short. In theory, these can process around 200 tons of source-separated food waste through anaerobic digestion. We think that our project could be part of this plan because it has similar aspects with what the government is already doing, but is more efficient from the output point of view. Food waste from the commercial and industry sector can be a crucial resource because it can be easily separated at the source, and the Environmental Protection Department mainly considers companies in this sector as the main source for the early plants. The main difference between our process and the adopted ones is that, as suggested by a study from Cornell University, is to add a step before anaerobic digestion, which is called hydrothermal liquefaction. In general, this process works by decomposing long-chain molecules available in food waste to get bio-crude oil and other products thanks to high pressure and temperature. The first step consists of loading the reactor with deionized water and heating it up until a high enough temperature is achieved to pressurize it in a way that it's kept liquid. To be sure, we chose a pressure which is around 10% below the vaporization one. The amount of water to be loaded at first is around 1 liter for every 20 grams of food to be processed. Then, the biomass is put in room temperature water with the same proportion, which is 1 liter to 20 grams, and is pumped into the reactor. In this way, the drop of biomass water mixture's temperature is negligible and the reaction can start as soon as the second part is loaded. So in total, we would need about 1 liter of water for every 10 gram of food waste. During all the reactions, which lasts about 20 minutes, the mixture will be continuously mixed by a magnetic agitator. When the time is over, the temperature is rapidly decreased in order to stop the reaction, and it will be possible to collect its output, which is bio-crude oil, an aqueous phase, and a negligible solid. As shown in the graph, the proportions of the product change quite a lot when temperature and pressure is consequently changed. For our process, we have chosen a temperature of 200 degrees Celsius, which corresponds to a 2.5 megapascal pressure. In fact, these conditions produce very small amounts of solid residue, and the production of aqueous phase is also much larger than the one of bio-oil. Even if bio-oil can be a very big resource, its usage relies a lot on its characteristics, which can change a lot with different temperatures or reactions. The biggest advantage of our plant is that it's very elastic. In fact, in order to change the proportions of the product's form, we only need to vary the temperature and the pressure. After performing hydrothermal liquefaction, the two major products, aqueous phase and bio-crude oil, are easily separated thanks to their different densities. The aqueous phase is then treated with anaerobic digestion in the way that we've explained before. As you can probably imagine, the amount of water needed by this plant is very large, but luckily it can be reused because it is only a medium in the reaction. Our idea is to get water from the sea. First, we will have to physically filter it in order to eliminate insoluble impurities. Then, we need to eliminate all the ions to get deionized water. The way we have chosen to do so exploits the ability of some organic compounds to selectively react with anions or cations. Here are some examples of the reactions that will take place in this filtration system. To compare our plant to the existing one, we have chosen to do a simple cost analysis. The existing plant has 200 tons of food waste input per day and is able to produce an energy surplus of around 14 million kilowatts hour per year with an efficiency that varies from 20% to 70%. The major process of this plant is anaerobic digestion with the elimination of inert residues from the food waste input. For our plant, which will include inert residue separation and hydrothermal liquefaction as a form of pretreatment, we can assume that the energy produced from biomethane is also around half that number, considering our input is half that of the existing plant. Although only 87% of our input is going to undergo anaerobic digestion, the addition of hydrothermal liquefaction, which breaks down large molecules and its cell wall structure, can raise the efficiency of the digestion by around 10 to 20%. Moreover, the 4,015 tons of bio-crude oil produced by this process has a market value of around $1,783,000 US, which can also make our plant more profitable. Although there are existing plants that focus on converting food waste into energy, we believe that it is possible to integrate them with hydrothermal liquefaction. Hydrothermal liquefaction can be added into food waste treatment plants because it is very flexible in terms of being able to produce feedstock for anaerobic digestion in addition to bio-oil, and allows for different forms of energy carriers to be produced for use in different